Welcome to Chapter 2, Section 1, Relations and Functions. And so during the hot days of summer and fall, we see a relationship between the time of day and the temperature. So in general, what can we say about the temperature as the time of day goes from morning to noon? Well, so from morning to afternoon, it gets hotter, right? It rises, gets hotter, temperature increases. So can you predict a relative temperature for 2 o'clock this afternoon? So will it be cooler or hotter at 11 o'clock tonight? So maybe at 2 p.m. this afternoon, 70 degrees, but at 11 p.m., it's definitely going to be much cooler. So we could say about 50 degrees. It's going to be cooler at 11. So if we call X temperature, if we call X time and Y temperature, we have what's called an ordered pair. So this represents the relationship between time of day and the temperature at that time. So when we have a set of data, we have a relation. So we can have a couple sets. So we can say, maybe at 8 a.m., right? So time of 8 a.m., our temperature could be 60. We said at 2 o'clock this afternoon, so that's 14 military time, maybe 70. At 11 tonight, at 2300 hours, we could say it's 50. So here we see a relation. So increasing and then decreasing. So the domain is the X value, and it's going to be graphed on the horizontal axis. So domain is where you live, and ideally you want to live in a large, flat, horizontal house with not lots of stairs so you don't trip. And then range is going to be the Y value, and it's graphed on the vertical axes. You can think of this as like a mountain range, how it's vertical up in the air. So the Santa Monica Mountains are going straight up. Range is your Y value. So we see here, graph the relation -3, 4, 2, 5, 0, 6, and -4, 1. So this is a relation, so remember to label the points. So first up, -3, 4. That's right here. So it's -3, 4. And then we have 2, 5. 0, 6, and -4, 1. So we see there's some sort of relation here. So if we wanted to make this continuous, it'd kind of look like a upside down, a sad face. So discrete versus continuous. So discrete is like a light switch. You turn it off and on. It only has certain points where it exists. So an example of this is if you are selling lemonade. So if you sell one lemonade, that's how much you make. If you sell 2 lemonades, that's how much you make. Graph B is like when you go to a store and you're trying to buy something by the pound. So maybe like some oregano by the gram. Well, you can have 2.2, you can have 2.3 ounces, 2.4 ounces. It's this whole continuous spectrum. Because you don't have to go in whole numbers, you can literally take 2.001 ounces and you still have to pay for the 0.001. I also think of this as like a dimmer switch. So it's not just off and on, but there's a wide range of light. So you can get brighter and brighter until it's completely on. And just remember domain and range. Domain is all the X and range is all the Y. So we can try this one. What's the domain and range of each function? So here the domain, X, range, Y. So the domain is going to be my X value, so -4, -3, 0, 1, and 3. So my X values are going to be the ones I highlighted. Those are my domain, while my range is my Y. Alright, so the Y will be -2, 1, 2, 3, -2, but we only have to write it the -2 once. So I'll write -2, 1, 2, 3. I only need to write that -2 one time. Alright, up here, don't forget, so we have X, Y. Let's find our domain. So domain is going to be all our X characters. So that's 3, -2, -3, and 4. And my range is going to be my Y. So my range is going to be -5, 5, -2, and -2. But I only needed to write it once. I only have to write it once if I have a repeat. -5, 5, -2. We also can diagram the relation. So recognize this and know how to map the domain and range. So for instance, if I had So this is mapping 4 different pairs. So this is -3, 4 as far as the coordinates, 2, 5 coordinate, 0, 6 coordinate, -4, 1 coordinate. So this is showing what this graph's mapping would look like. The mapping of B, let's see. So here's the domain, here's the range. So my domain is -3, -2, 3, and 4. My range is -5, -2, and 5. So we can map it. So I can draw, let's see, 3 goes with -5. So it goes this way. -2 goes with 5. -3 goes with -2. It's a different color. There. So -3 goes with 2. And then 4 goes with 2. So notice that each one of these x's have their own y, right? So this, it's not like this 3 was pointing to -5 and 5, because then it'd be pointing to 2. They each are only pointing to 1. So a function is a relation in which each element of the domain is paired exactly with one element in the range. There's no repeater of x. So here, let's see if we have any repeating in the x. So we have 3, 8, -2, 5, -7. There's no repeaters, yay! It doesn't matter if multiple have the same y value, as long as a single x does not have more than one y. No repeaters, so this one is a function. So function means each x only has one y value. Alright, next one. So let's check it out. So this -4 has 2 y values. Also -2 has 2 values. So it should look like this for 2 y values, because this is also -2. So we have 2 things that are repeating. So -4 and -2 are repeating, right? So each x value has more than one y value. So then we say it's not a function, because functions only have one y value for a given x. Just this one alone, we have 2 values for -4. So this -4 has 2 points. Right? I can't have 2 points for a single x. Last one. Check it out. We once again have 2 x values. -2 repeats. So it's not a function. So the one-to-one function means each element in the domain is exactly with one y. Alright, so 1, 2, 3. But the reason it's called one-to-one is every single x has a y, but maybe not every y has an x. Check that out. C is all alone. An onto function means each element of the range is an element of the domain. So C has 2 different x's, B has an x, D has an x. So what this means is all of these characters have an x. What if I had another x over here? That was 5. So all the y's are taken care of. Maybe not all the x's. A one-to-one is both, right? So each x has exactly one y, and each y has an x corresponding. So everything is taken care of. So this is mapping. So here, this is not a relation, so I'd like you to think y. So 3 has more than one y value. More than one y value. All right, let's try it out. Relations, ordered pairs, functions, domain, yikes. Okay, if we look at the graph and decide if it's a function, I wonder how we can do that. Well, we know that each x can only have one y value. So if I select x equals 0 on this graph, notice that x has a y value. X equals 0 has a y value of -3, of 0, and maybe a little bit more than 3. Has 3 distinct y values. 3 y values for x equals 0, so we say it's not a function. But here, if I circle x equals 0, it only has one y value. If I pick x equals -2, only one y value. X equals +2, each of these only have a single y value. So you can do something that's called the vertical line test. If the vertical line test passes through more than one x, it's not a function. So if it cuts across the graph more than once, it's not. If it doesn't, if it doesn't cut across the graph more than once, if it does not, it's a function. If it does cut across, it is not a function. So here I only have one crossing, but here I have two crossings. So this guy, every time I do a vertical line test, I only have one crossing, versus over here, I have two crossings. Here, every single point, I only have one crossing. Alright, so function notation. The first example we discussed, time of day and temperature. So time of day, time, and temperature. Alright, so keep in mind, temperature is y, time, x. The temperature depends on the time, or y depends on x. Early morning and evening are generally cooler, and mid-afternoon is hottest. So the variable that is dependent is y, and independent is x. Dependent is the y variable, independent is x. But we also can write y as f of x. So notice that the expression f of x replaces y in function notation. So just an example here, I could say f of x is equal to 3x minus 1. These mean the same thing. Y and f of x mean the same thing. Alright, so the independent variable is going to be time. So I'd say that's y. The dependent variable will be temperature. And that's going to be my y value. So what's the domain and the range? Well, here in example 2, we say that the dependent is going to be y, and the independent, independent is x. So what's the domain and range of x? So the domain is x. What numbers can I plug in for x? Well, I can say all real numbers. That's what that R means, is all real numbers, because notice we have a function, and if I would graph it, I could pick up my pen. I wouldn't have to pick up my pencil and check it out. There's all my numbers. Actually, it's going to look like that. This guy. That's what it looks like. So the y, so here in this function that we're looking at, the dependent variable is y, so what will y, doesn't matter what y will be. Depending on what we plug in for x, y can be any number. So we say all real numbers. Because I could plug in I could plug in 0 for x, and y will be -1. Plug in 100 for x, and y will be 299. Plug in -5,000 for x, and y will be -14,999. So it's all real numbers. That's how we write that. An equation line expressed in function notation, maybe f of x equals 2x minus 3. So what is f of -6 in the above function? It's asking what is the y value when x is 6. Oops, -6. So let's see, plug in 2 times -6 minus 3, because I'm just plugging in for f. F of x equals 2x minus 3. So 2 times -6 is -12. -12 minus 3 is -15. Given the function f of x equals 2x squared minus 3x plus 1, find the following value. So I want you to pause the video, try this out. Alright, so 2, I'm just plugging in -2 for my x. So first up, I need to follow the order of operations. So -2 squared is going to be 4. Let's see. -3 times -2 is plus 6. 2 times 4 is 8. So 8 plus 6 plus 1 is going to be positive 15. So notice the negatives cancel each other out when you square it, and then this negative and this negative cancel out. Alright, now let's plug in 3a. So I have 2 times 3a squared minus 3 times 3a plus 1. So here, since this is being multiplied 3 times a, they're being multiplied, I can distribute out the square factor. So I have 2 times 3 squared times a squared minus 3 times 3a plus 1. So a squared is still a squared. 3 times 3 is going to be 9. So this is 2 times 9a squared. So 2 times 9 is going to be 18. Negative 3 times 3 is negative 9a plus 1. And lastly, the volume of a sphere with radius r is given by the function v of r is equal to 4/3 pi r cubed. So find v2. So v of 2. So I'm plugging in 2 in place of my r, and that's going to stand for my radius. 4/3 pi 2 cubed. So 2 times 2 is 4. Times 2 is 8. That's what 2 cubed is. 4/3 times 8 times pi. I did that so we could get the numbers next to each other. So this is 32 pi over 3. This represents the volume of a sphere. It's in units cubed. Awesome. So that concludes the first lesson. Let me know if you have any questions. Feel free to come to bonus or email me. Thanks. Bye.